Hi, my name's Marina, and I'm going to talk to you about enantiomers. So let's say we had a mirror. On the left side, we're going to draw a molecule called limonene, and on the right side, we're going to reflect that molecule over so it's a perfect mirror image of the one on the left. Now notice that both of these molecules are called limonene, but the one on the right is an enzyme responsible for the smell of lemons. Now the one on the left is the mirror image of the one on the right, and yet it's responsible for the smell of oranges. How can this be? Well, the answer is that they're enantiomers of each other and they have different properties. So, what are enantiomers? They're molecules that are mirror images of each other but are not superimposable. We'll talk about what that means later. They're differentiated by labeling one as the R molecule and the other as the S, and they're stereoisomers, meaning they have the same molecular formula, the same configuration of atoms, giving them the same IUPAC name, but they differ only in the spatial arrangement of their atoms. So enantiomers seem pretty cool, right? But they can also be really serious. Let's look at the example of thalidomide. The R molecule was sold as a common drug in the 1970s because it helped cure nausea, but the S molecule actually causes birth defects. Scientists did not realize this until over 10,000 infants were affected. Now you might be wondering why the mirror image of a molecule can act so drastically different, and you have to remember that molecules are 3D objects in space. If you were to take this 3D ball and stick model and reflect it over the axis, you'd produce two enantiomers. Now if you were to take the enantiomer on the right and try to rotate it to match the one on the left, you'd see that it's not possible. If you were to rotate it clockwise so that the green would remain on top, blue would be in the center, and yellow would be on the right, you'd see that the orange and the red can never match up with the original molecule. This shows that they're not superimposable, meaning that if you were to take the rotated enantiomer and place it on the original, they could never match up perfectly and our bodies would react to them differently. Enantiomers are all around you and you may not even know it. For example, amphetamine, which is a central nervous stimulant, is sold to help treat narcolepsy, ADHD, and obesity. The S enantiomer is 3 to 4 times more potent as a stimulant, while the R version produces more adverse cardiovascular effects. Another common enantiomer is ibuprofen, which is a popular pain reliever. The S enantiomer is actually what helps relieve pain, while the R enantiomer is inactive in the body. Now, you might be wondering if there's a way to separate enantiomers, and there is, through chiral resolution, a process which varies from molecule to molecule. There's no set way to separate enantiomers, which means scientists have to do a lot of difficult research on if enantiomers form, what they do, and if they can be separated at all. This also makes it costly. But nevertheless, it's important that we understand enantiomers. They often form together naturally, but can have important, adverse, life-altering, or even just plain cool consequences.